scrap piles. They're ugly, dirty places, often infested by mosquitoes and other pests. Worst of all, there may be tires there that didn't give you your money's worth. No wonder a scrap pile is something only an engineer could love. But maybe the engineers have something after all. Because if you know how to read it, every scrap tire has written in it and on it the history of its life. The trained, experienced eye can spot the reason why a tire had to be scrapped in the first place. Not just the obvious reason, like a run flat, but the more subtle things, which may have made the tire a candidate for a run flat. Things like misapplication, choosing the wrong tire for the job, or mismounting, tearing the bead and damaging the tire before it ever touches the road. Mismaintenance, overloading, improper inflation, faulty alignment, and so on. Misfortune, having the bad luck to run into road hazards like rocks, nails, or potholes. And mismanufacturing, getting a tire that's irregular in materials or workmanship. If you know what caused your tire to be removed from service, you may be able to help prevent that kind of removal in the future through better tire selection, better mounting procedures, or better tire and equipment maintenance. Bridgestone Firestone recommends that you evaluate your scrap tires as soon as they're pulled off the vehicle and demounted. That's because some of them may be able to go on giving you useful service if they can be repaired or retreaded. And experience shows that the longer tires sit on the scrap heap, the less successful repairing or retreading may be, because the longer they sit, the more time rust has to do its dirty work. But more important than that, the faster you get information on what's killing your tires, the faster you'll be able to take steps to stop it. That'll keep more of your tires on your vehicles where they make money for you, instead of in your scrap pile where they cost you money to store and dispose of. One of the most important parts of effective scrap tire analysis is good record keeping. Your Bridgestone Firestone representative has forms which you can use to log your scrap tires. There's a place to record the manufacturer of the casing, the DOT number, and lots of other information. The DOT number can be decoded to tell you which factory made it, and the last 3 digits tell you the week and year the tire was made. Important to know if you need to make a warranty claim. You may also want to use tire chalk to add your own number for quick identification if the tire has to be stored for a while before you scrap, repair, or retread it. If the casing has been retreaded, you'll want to record that too, including the number of times it's been done. Make a note of the tread pattern, size, ply rating, and remaining tread depth, and then look at what caused the tire to be pulled off the vehicle. Do a thorough check of the whole tire, not Let's take a look at some common damage conditions and their causes. We'll start with misapplication. Here's a tire that was designed for on-highway use, but the chips and cuts we see tell us that this tire has probably been run off the road. The off-road surface has chipped and cut the tread, removing chunks of it. And because so little of the damage is on the right or left shoulder of the tread surface, this tire is probably also a victim of mismaintenance. The inflation pressure was probably too high for the application. The result is that the damage is worse in the middle of the crown area, because it was the area most in contact with the road. And we see grooves and scratches that run in the same direction as the tire would turn, indicating that at least once the vehicle got stuck and this drive tire was spun. Nevertheless, this tire is probably retreadable. Here's another example of the same problem, an on-highway tire run off the road. The damage is even worse here. We can see a broken, rusted cord sticking out of the tread surface. When we probe this area, we find that the tread is already becoming separated from the casing. And again, most of the damage is localized in the middle of the tread, so this tire may have been run overinflated as well. Your retreader may have to buff this tire to confirm it, but this casing is probably not retreadable. Finally, this tire has lots of chipping, but the chips are pretty well scattered across the whole tread surface. That means that at least the tire was probably run at about the right inflation pressure, even if it was on the wrong surface. And we see that the chips have become so severe that in one place, the top belt is exposed. It's already begun to rust, which may cause a separation, and eventually the casing will be ruined. Once again, your retreader can advise you as to this tire's retreadability. So, just by looking at tread surfaces, we've been able to identify tires that have been run on the wrong surface, at the wrong inflation pressures, and which have been spun when the vehicle got stuck. Now, here's a tire that shows lug base cracking. This can result from a combination of high torque, high load, and high heat, and it may also be aggravated by underinflation. If the cracks don't go too deep, like the ones we see here, the tire can probably continue in service. And this tire is just about ready to be retreaded anyway. A new cap could make it ready for quite a few more miles. If lug base cracks extend more than a few 30 seconds deep, it may be a sign of misapplication or mismaintenance. At any rate, it's a good sign that you ought to consult your tire supplier for help in diagnosing the problem. Another kind of mechanical damage that can appear on tread surfaces is rib tearing. This is usually the result of misuse or careless use rather than misapplication. Running over curbs or railroad tracks, especially at odd angles, or other severe impacts can cause rib tearing. And it can be worse when vehicles are operating at high ambient temperatures and have to make lots of sharp turns, generating high side forces. Generally, this happens when the tires are relatively new. We can see that chunks of rubber are being torn off the surface of the tread because the torn surface is rough and striated rather than polished. Depending on how severe the damage and how deep the tears, tires with rib tear may have to be removed from service, but most casings are retreadable unless the tears extend to the steel belts. Another similar condition is defense groove tearing. Like rib tearing, it often results from severe localized impacts with curbs or rails. In this case, though, we can see that the tearing has damaged only the defense groove itself and has not extended to the ribs or penetrated below the tread. This tire can continue in service so long as damage does not go all the way to the steel belts. This tire is a retread, but for some reason, along this edge, the new tread didn't get bonded to the casing properly. This loose tread condition has resulted in the cap being worn completely smooth in some areas. The constant rubbing of the loose cap against the undertread has caused both to be polished smooth and shiny, as you can see here. This is a tire that needs to be removed from service so that retreading can be done properly before the casing is lost for good. And while we're talking about retreading, we should also mention that improper repairs can cause plenty of problems as well. Here's a repair unit on the inside of a tire that basically looks okay. The bead indicator arrows are pointing to the beads the way they're supposed to, and the unit appears to be secure. But when we turn the section over, we can see the hole that caused the original problem, and something else as well. Improper skive preparation technique led to insufficient bonding between the retread stock and casing, and the repair on the tread side did not hold. So on this repair, apparently only about half of the job got done. You should return it to the repair shop for replacement or credit. Here's another halfway job that resulted in big trouble down the road. In this case, a nail hole was repaired on the inside, but the hole itself was not plugged. That permitted water and air to get inside, causing rust that completely destroyed the belts and casing cords, with the result that you see here. A sloppy repair resulted in an on-road failure and in the total loss of an otherwise good casing. In this case, the bead arrows aren't pointing to the beads at all. No doubt that this is an improper repair which could fail without warning. You should return it to the repair shop for replacement or credit. While we're on the subject of training, the Rubber Manufacturers Association and the manufacturers of repair materials and equipment provide lots of brochures, charts, and materials that you can use to help yourself learn about the proper use of repair units and equipment and repairability of various damage conditions. Here's one that looks okay, on this side anyway, but by the time we get to the other side of the repair, we see that only the edge of it is attached, and we can slide the probe underneath the whole right side. This is called a bridged repair, and probably occurred because the repair unit was not properly applied. Most likely, it was applied with the beads in a spread rather than relaxed position. It may not have been stitched properly. The edges may have been stitched down before the center, or some other incorrect technique may have been used. Once again, it's pretty clear that this repair is unsatisfactory and is bound to cause problems. You should return it to the repair shop for replacement or credit. Finally, here's a repair that's almost, but not quite right. The repair unit appears to be applied properly. On the outside, on the shoulder and sidewall, there's a slight bulge. The Commercial Vehicle Safety Alliance North American Standards Out-of-Surface Criteria specify that a section repair-related bulge must not exceed 3/8 inch in height. Our repair test gauge, like this one from the American Retreads Association, shows that it's well within acceptable limits for a repair-related bulge. But the repair is not properly marked with the customary blue triangle, and that means that without demounting the tire, nobody can tell whether this is a repair-related bulge or a damage-related bulge. At roadside inspection, this missing triangle could cause a lot of unnecessary hassle and lost time just because the person doing the repair failed to finish the job. And what is that DOT inspector looking for anyway? Well, probably something like this. In this case, there's a small cut in the sidewall, but sometimes all you see at first is a bulge, like the one we just saw. But when we peel back the sidewall to see what's underneath, we see that several of the cords are broken. This probably is the result of some sort of impact damage. And then, looking at the underside of the flap of sidewall we've removed, we see that the frayed ends of the cords have been rubbing against the sidewall. They've actually gouged out a little depression in the rubber. They also made the surface of the sidewall bulge a bit, sort of like the way your thumb swells if you smash it with a hammer. This doesn't look too bad right now. If caught early enough, it may even be repairable. But it has the potential to turn into something really serious, as we'll see. When damage like we just saw is neglected, it can get worse and may end up like this. The cut in the sidewall allows air and water to get inside. Water travels along the cord filaments, an effect called wicking. This causes rust to spread, sometimes far from the initial entry point. The broken cords are no longer carrying their share of the load, and as the intact cords get rusty, they lose strength and become brittle. They too are liable to break over time. The result can be the dreaded zipper, which can cause a catastrophic sidewall failure and can be very dangerous to anyone who happens to be nearby when it occurs. So just a little impact can be the start of big trouble. Tires like this should be removed and evaluated when the impact damage is first seen. This time we've got a blue triangle on the sidewall, properly indicating the location of a repair. Inside we find a repair unit that appears to have been properly installed. Everything looks good. So why does this tire have an enormous zipper? It may be that the damage was done long before the repair was applied. If this tire was run for some time at less than recommended inflation pressure, it could have severe sidewall fatigue as a result of abnormal flex damage to the body ply cords. This can produce the kind of result we see here. The repair indicates that the tire lost air at some time in the past, and from what we see now, the repair unit was too late to save this tire. And here's another example of severe run-flat damage. The inner liner is in tatters and is separated from the body ply. The sidewall has also split open and become detached from the body ply nearly all the way around. Something caused this tire to lose air, and as we probe around, we find some damage, but not what we're looking for. Finally, here it is, a large hole with a concentric circle pattern around it. From the look of it, the likely culprit was a hex head lag bolt. If the driver had been aware of the damage or had noted a slow air loss and stopped immediately, this might have been a fairly routine repair job. Instead, this tire is trash. In the last case, the excessive flexing caused by running flat resulted in the sidewall splitting open and separating from the body ply. Here, excessive heat from the run-flat condition caused the tread and belt package to separate from the casing. A look inside shows us that the inner liner has split and peeled away from the body ply. There was a fair amount of usable tread on this tire when it was removed. Now, neither the tread nor the casing is usable. But not all heat damage to tires comes from heat generated by the tires themselves. Sometimes the heat comes from the outside. Notice that the bead nearest us is thoroughly scorched, but that the other bead is not. One of the common causes of this is an overheated brake drum, combined with a lack of airflow around the bead and brake drum. Brake drums are connected to the wheels at only one end, so brake heat is conducted primarily to one bead. In addition, this bead has less airflow around it to take away the heat. The other bead may look completely normal. In this case, the heat was so severe that the ends of the nylon chafer have melted, and the chafer and body ply have come completely loose from the bead bundle. Though there are several different causes of this type of damage, a dragging brake, one suffering from green lining swell, or a malfunctioning automatic slack adjuster could cause the drum to overheat, creating this problem. If we cut a section from a tire with this kind of damage, we can see that this bead area is not repairable and that the rubber is no longer springy and resilient but hard and brittle. The bead bundle, ply turn-up, and chafer may look okay, but this bead is no longer able to fit tightly against the wheel to provide a good seal. And not all bead damage comes from heat. Mismounting tires, incorrect rim size, and careless use of mounting equipment can tear chunks out of the bead rubber. If they're small and do not expose the steel bead bundle like the damage we see here, the bead should be repaired immediately to provide an effective airtight seal. On the other hand, large serious damage like this that extends all the way down to the steel cord cannot be repaired, and the casing must be scrapped. This is a big reason why careful mounting can contribute to overall tire economy. And damage near the bead may not show up right away, nor may it be as obvious as the torn-up beads we just saw. Over time, the ends of the body plies, which turn up around the bead, can separate from the rubber surrounding them, forming tiny cracks like the one you see here. Over time, these cracks will grow and work their way out to the surface of the tire, exposing the cords to air and water, causing them to rust. This ply-end separation is fairly small, but the one on the other side of this section extends all the way to the tire surface. Excessive stress, flexing, and heat in the bead area, and the areas adjacent to it, can be caused by improper bead seating, improper rim size, improper inflation, or impact damage. The damage looks very small on these sections, but when we look at a tire like this one and use a bead expander, we can see that in this case at least, this ply-end separation is a pretty serious problem. The tire must be removed from service, and the damage is too extensive to repair. As we said, ply-end separations can also result from impact damage in the ply turn-up area. Here, a sidewall snag has started the process, which once begun will eventually make the tire look like the one we've just seen. This tire will have to be scrapped. And here's one that looks like it might be a ply-in separation, but isn't. The way we can tell is that as we probe the area, we see that the crack does not go all the way to the ply ends. All we see is rubber inside. This is what's called a bead area flow crack. It may be the result of improper rubber flow during the manufacturing process. In most cases, especially if the crack is small, it is harmless, and you can go on using the tire. If the crack is large or grows larger over time, you should remove the tire from service and consult your tire supplier. Besides heat, the outside world can supply lots of other hazards. We've seen examples of tread area punctures, but road debris and potholes can also cause plenty of damage to sidewalls. Here's a tire with a couple of pretty serious sidewall snags. The rough surface of the edge of the loose flap and the striations in the damaged edges indicate that these sidewalls were cut by a road hazard rather than damaged by impact. Because these cuts weren't repaired, air and water got inside, causing serious rusting to the cords, rendering this tire neither usable nor retreadable. A really large object, besides destroying the sidewall, can leave behind damage that gives us a pretty good idea of what probably happened. Here, the shape of this huge sidewall cut suggests that an object similar to this screwdriver may have caused the damage we see. As we roll the tire toward the screwdriver, we can see how the blade traces out a pattern very similar to the damage we see in the tire sidewall. The striations in the damaged area help us to determine the direction the tire was traveling at the time of damage. And with this much damage, this tire cannot be repaired and must be scrapped. Here's one that looks like a sidewall snag, but is anything but. Notice how closely the edge of this damage parallels the radial body cords. The damage does not penetrate all the way to the steel cord, and the inside of the damaged area is very smooth, unlike the inside of a snag. This is an open sidewall splice, which may be a manufacturing anomaly. The tire must be removed from service, and you should consult your tire supplier for a replacement or credit. Our final category of damage is the one that's sometimes the most spectacular. A sudden violent impact to the tread area causes a break to occur in the body ply and inner liner, followed by the air pressure in the tire causing everything to push back out again. The belts are often ripped diagonally, and fragments are thrown through the opening by the escaping air, producing the familiar rabbit ear effect. Huge chunks of tread are missing, broken cords are a rat's nest of tangled wire, and fragments of torn belt and body ply are scattered throughout the damage area. A deep, sharp-edged pothole or some other kind of sharp-edged road debris is the likely culprit. There's no way to repair this damage, and sometimes no good way to avoid it, except by changing your route. Both overinflation and underinflation put a tire at risk for impact damage. Overinflation makes the tire too stiff to give the way it needs to. Underinflation allows the tire to deflect too much during an impact, resulting in damage to the tire's internal structure. Here's a telltale sign of serious impact damage. Impact with an object has caused so much deflection that the body ply has split between two radial cords and torn all the way through the inner liner. Incredibly, this sometimes is the only evidence of impact damage. An examination of the tread area may show no obvious problem. In fact, a tire with this kind of damage may even hold air pressure. Nevertheless, it's not usable or repairable and must be scrapped. That's another reason why you want to thoroughly inspect both the inside and outside of every tire. Even though the inside split runs all the way across the belt area, the tread damage may be quite localized. Here's a tire that's been hit hard by a relatively small object, perhaps a piece of pipe or rebar in the road. The tread's been severed, as have the belts. A flap of tread and belt material has been pushed all the way through to the interior of the tire. The body ply and the inner liner have been split, and the escaping air has pushed everything back out again. This tire must be scrapped. Finally, here's an impact break that resulted in one of those roadside tread rubber strips we so often see. First, there was a big impact break, splitting the body ply and liner and loosening a flap of tread. And then as the tire continued down the road in a run-flat condition, centrifugal force tore off a huge flap of tread and belt. The rough surface shows that the tread and belts were literally ripped apart. And as studies have shown, these scraps of tread along the roadside are more often the result of damage followed by a run-flat condition or a run-flat condition alone, not the result of faulty retreading. If the problem were retreading, we wouldn't see so much cord sticking out of those roadside scraps because retread rubber contains no cord. This brief look at various types of tire damage and causes is not intended to be complete, nor the final word on the subject. In your operation, you may never see the types of damage we've shown here, or you may have damage types we haven't shown. You may wish to consult industry literature or your tire supplier for help in evaluating and analyzing your scrap, and for ideas you can use to reduce the size of your scrap pile. The Tire Condition Analysis Guide, published by the Maintenance Council of the American Trucking Associations, is an excellent ready reference to a wide variety of tire damage conditions. And it also contains a good glossary of useful tire-related terms. Now, let's take a look at what we might learn from doing a scrap tire analysis. After collecting data on several hundred scrap tires, we noticed that the distribution of scrap doesn't match the distribution of tires in our fleet. Our 255-70R 22.5 trailer tires represent only 15% of our wheel positions, but fully 35% of our scrap. What's wrong? Are we overloading, using the wrong ply rating for the application, the wrong tread pattern, or what? A little more investigation, specifically into our trailer tires, shows that most of the damage condition that caused these tires to be pulled from service occurred in the sidewall area. Breaking the information down still further, we find that far and away the majority of these damaged sidewalls appear to result from curbing of the tires. And now we've really got some useful information. Perhaps we need a better driver training program to offset lack of experience or high driver turnover. And we may benefit by talking to our tire supplier about Metro-type tires with sidewall protector ribs. These sturdy ribs take the brunt of curb damage, protecting the sidewall, and most have ribs on both sides. When one set is worn away, you can reverse the tire to expose another set for continued protection. In any event, this kind of analysis can really help you and your tire supplier choose the best tire for you. Here's another analysis comparing patterns and positions. On drive axles, one tire model is hitting the scrap pile at about a 16% higher rate than the other. When we look at steers, we see that one model is producing a smaller proportion of scrap than the others, by 30% to nearly 70%. And we also see that one model is no longer being purchased. We know this because there are more of them in the scrap pile than there are on tractors. Scrap analysis can also show us how effective our retreading programs are. Here we see that fully 18% of our scrap tires have never even been retreaded the first time. Is there something we can do to increase our success? Maybe a different tread pattern or a different manufacturer is worth a try. Or maybe we're running tread depths down too low before we pull the tires for retreading, risking irreparable damage. And we see that very few of our scrap tires are on their third cap, probably showing us that few of our casings last long enough for that. When we look at the remaining tread depth on our scrap tires, we see that original tread depths are pretty low on virgin casings and pretty deep as we retread more and more often. This may suggest, in light of what we saw on the previous chart, that if we pulled original tires a little earlier, we might find that more of them could be retreaded. And it also makes us wonder if putting a third cap on is worth the expense, since so many of our third cap tires are being scrapped with so much remaining tread depth. It certainly doesn't look like we're getting our money's worth out of them. The place to learn about tire damage is in your own backyard, in your own scrap pile. The information it contains can be a valuable asset, helping you get more miles out of every tire and more miles out of every dollar you spend on them. Scrap tires may be a nuisance, but regular, thorough analysis of your scrap can tell you what you need to know to make your scrap pile as small as possible. If you have questions about scrap tire analysis, would like copies of forms you can use to record your results, or would like assistance in reducing your scrap, contact your tire dealer or Bridgestone Firestone Incorporated. We'll be happy to help.